So last time I told you that when you have continuous symmetry, you have immense freedom. And this freedom comes responsibility. In this particular case, you'll have two choices which are very aware of your life. What's good for yourself is not maybe good for your people. So there'll be ways of exploiting this freedom. One of them maximizes your own comfort, and the other one actually enables you to take care of all chaotic motions, not just one. So that'll be the drift of the talk. But before I get it, I have to clear up a few things about what happens to solutions you're used to now when you have continuous symmetries. So far we've assumed that only continuous parameter of dynamics is time. When we have more continuous parameters, the symmetries of solutions become interesting. So it was a discussion about symmetries of laws of nature, but as we already know from study of discrete symmetries, but also just from our experience, there is no reason why solution of equations of motion would have the symmetry of equations of motion. As a matter of fact, what's of interest to us, which is turbulence and chaos, the most interesting things are the ones that have no symmetry at all. They break all symmetries. So it's good to recapitulate again what kind of solutions you care about. Whenever you have a dynamical systems, counterintuitively, the first step is to find solutions which are not dynamical. Equilibria or stationary, steady or fixed point solution. So equilibria, they satisfy that at equilibrium point xq, so when there is no symmetry, that's a zero-dimensional, it's just a point. If you compute velocity in any direction in d dimensions, that velocity is zero, so if you're stuck there, you'll always be there. That's equilibrium. If you add continuous symmetry G, if x of q is an element of fixed G, which means all points in a state space which are not moved by dynamics, by the group transformations. An example. Suppose I have a three-dimensional system like Lorentz systems. So there's an x and y and z. Another continuous symmetry is the one that says anybody on this circle that goes around z in any xy plane, these are group orbits, these are equivalent states. So group orbits are one-dimensional in this case, if you have just one parameter, except on the z-axis. That's an invariant subspace. On that axis, there are just points. So if it sits here, this is dimension 0. Some point here, the group won't change it. Now, what's nice about this invariant subspace is that we have shown already that if you're in the subspace, the dynamics doesn't take you out. So if you're there, you stay there forever. So that gives you already nice sort of classifications of possible motion. Motions which are in the invariant subspace, group doesn't move them around, produce copies over, and the other motions that come in families. And then, of course, if you have more parameters, you might have subgroups, and there might be a whole classification of things. Right now, we're just thinking of SO2, which has only one parameter. So this is an example here. Now, if you find an equilibrium solution any place, and it has a property that nothing happens at this point, then by group transformations, there is any other point here, which is g of xq, that's also a solution. So when you have a continuous symmetry, even though you think you have only one fixed point because you did something and computed one fixed point, typically you looked at some antisymmetric subspace or something. So typically you were looking at some, let's say, wave function, and you decided that it should look antisymmetric. So the moment you impose antisymmetry condition, you pick out one solution because no other solution is the same in the family. So the other solutions are in the conjugacy class, so they're like shifted solutions, they look like this. So if you will mistake a solution for another solution because it'll be off the center, you won't realize that it's there. So that's what group orbit, it's all the possible shifted. So the moment you have symmetry, there are no equilibria as isolated physical solutions unless they sit in invariant subspaces. There's a one-dimensional family of them. So it's different. And they're all physically equivalent. The same thing just moved around. So equilibria have changed their nature in presence of continuous symmetry. And then comes a next question. You say, oh, but that's just a periodic orbit. But it's not periodic orbit because nothing is changing. But what you could do is you could look at the system where you are here, that's your group orbit, but your group tangent is the thing that's always tangent at a point to the group, so I call it T, coincides in its direction with the velocity. So T at x of q and v at x of q coincide. Now what that means is that you have a solution where you don't stay put, but you move on a group orbit. And that means that that solution is the same solution, but just moving in time. So that's called a traveling wave, or has many rotational wave, all kinds of names. But that's a very typical thing in presence of continuous symmetries. And it's called relative equilibrium. And because everybody invents this, sooner or later it has 100 names or 20 names in English only. Because engineers will invent a name and celestial mechanicians everybody will invent a name for this. Now relative, this has a good pedigree for once. This word was introduced by Poincaré to explain precisely that, and he is the father of the subject. Qualitative theory of differential equation. So there is nothing to discuss. This is relative equilibrium because Poincaré said so. So now my colleagues think that this is a periodic orbit because it behaves like periodic orbit. It goes in time and runs around. That's what periodic orbit does. So if there is some, by symmetry, the moment you have chosen this tangent vector, you have a statement saying that velocity at point xq is proportional to the tangent at point xq. In general, there might be 3 or 7 or 8 or 20 parameters. If you're in SU3, it'll be 8 parameters. So there is a label here saying move in this direction, move in that direction. And then there will be a velocity. So this is dimensions length over time. This object, this is just a matrix multiplying dimensional, multiplying a position. So this is dimension 1 over length. So this thing is dimension 1 over t. So this has to do with frequency. So this is a phase velocity. This is how quickly, inverse of this is, how quickly you come back, especially if you decide that this thing is, let's say, in units of 2 pi, etc. So that's called phase velocity. 1 over this, or maybe 2 pi over this, velocity, magnitude is speed, and 2 pi over this is how long does it take to come around. So you can mistake it for the period of this thing if it makes you happy, but that's not what it means. That's not the important thing. So, relative equilibrium is not periodic orbit. The reason why it's not a periodic orbit, because as you'll see in a moment, periodic orbit is one dimension bigger. So there is a difference. Without continuous symmetry, you had equilibria, which are one-dimensional solutions, zero-dimensional, and then you had loops, periodic orbits, which are one-dimensional. The moment you had continuous symmetry, everything increases its dimension. So what's a periodic orbit? That's a thing that I start someplace at x. I have my equations of motion move me around by integrating them. And then this is a very special kind of orbit that after time t, which is called the period of the orbit, now this really means a period, you come back. So that's a periodic orbit. But because we have a continuous symmetry, once we have one of these orbits, we can just move it around and move it around. So it gets a little harder to draw, but associated with this point is its group orbit. And as I go someplace else, I will generically end up on a different group orbit. So, I'll go further away from the center, something will happen that'll look different. So there'll be a thing that, because I was thinking about this in Göttingen, which is the mother of modern mathematics, and the beer was good and sausage was good, so I call this a whoosh. What happens is actually every point owns a little circle, and if it was 7 dimension, it would own a 7 torus. And I can't draw this, but I can still draw that. So the moment I find one periodic solution, there's another periodic solution which has a point on it, which is g of x, how long it took me over there. And they'll just sweep, this little disk will sweep a surface which will have a varying diameter. So we'll get fat and thin and we'll do God knows what. So this is a 2-dimensional surface, the torus. But it's distorted because dynamics distorts it. It's not your bagel. The way it's generated is that dynamics sweeps through the state space on one unique trajectory. If you have one unique starting point, your law of motion. But with it, it carries a little disk which changes its radius as you go around. And it's not, it turns out to be very deformed. Group orbits are not pretty to look at, it turns out, in nonlinear dynamics. So, dimension of periodic orbit is actually 2, because these are all physically equivalent states. But it just so happens that if I'm not careful, I'll just think I have one of them. Same issue as with equilibrium. If I don't align it correctly, I might mistake different copies for different orbits. But they're all the same. They're just related by symmetry, and they're physically identical. It's just that in your coordinates, they're changing different. So the reason why this is worse, because pretty soon we'll be slicing it, so I can't resist slicing sausages. Let me ask yourself the same question as before. Okay, but what happens if I actually have a velocity which is not perpendicular to the group orbit, but it has some direction along the group orbit? Here I had something where my velocity was such that I had no motion along the group orbit at a point, I just went around some way. What if I change that rule? What happens? So what will happen then is that the orbit, instead of just going around like this, it will start winding around, go around this object, and then land on the group orbit of initial point, and that will be called relative periodic orbit. And that has a property, I'll write it here, that if I start at x, I start at this point, I let time run, time t later, I'm in the same state. So, if I was swimming, time t later, I'm in the same position, but I've moved in the swimming pool. So in a continuous symmetry direction, something happened, but my state is the same. So I'm on a group orbit because I can just take the swimmer and put him back. or harness them or something. So there is a group transformation that said that I get here, then I apply a group transformation which costs nothing, it's a symmetry operation, and I get back. So now, this is the correct notion of periodicity in presence of continuous symmetry. All periodicity happens on tori, not on loops. And the dimension of tori has to do with number of continuous dimensions. We have this intuition that rotations are circles because, that's how we think. In a plane, the thing is a circle. But in general, the problem is nonlinear. It has lots of terms. So this is correct thinking for linear problems. But for nonlinear problems, and I'll come back to it, it turns out that different terms contribute different motion as you move around the group orbit. And they produce very complicated structures, which are topologically circles, but the way they're embedded in your state space is like a piece of chicken wire, and it's very complicated. That's actually the whole problem. It makes it hard that they're not circles. If it were circles, this would be just half of a lecture, and we would move on. But it turns out you'll see pretty soon they're uglier. Okay, so these are periodic and relative periodic orbits. So these are kind of solutions that you have. What I do now is I write a Newton solver or some solver. I had one that was finding periodic orbits without presence of symmetry. I think a little bit more, and I realize when I have a problem like this, I have to compute two numbers because G is typically parameterized by some angle. So in simplest case, G is written as, let's say, in real representation as cosine, sine, theta, theta, if you have some simple Fourier mode. So G is something parameterized by an angle. So you say, fine, I will now work, and I'll produce a table which says, I have a periodic orbit and it has a name je de or something. And then I list its period of je de, and I list this angle, theta. And then I list stability, the largest multiplier for periodic orbit, complex real parts. And I give you this information, I give you a point on it, and then you know all about this periodic orbit, and you might be able to use it in some calculation later on.